Now what if we want to use two cameras, not one camera? Yeah. Why two cameras? Two cameras, even though you can do it with one camera too, but typically you extract 3D information from the world using two cameras. Yeah. And so when we do stereo cameras, there's going to be a little bit extra information and assumptions that we need to have compared to single cameras. For example, we need a coordinate transformation between the left. Question? Do we have a question? No. If we have two cameras, one thing that we need to do is to know the transformation between the two cameras. How far is the right camera from the left camera? Yeah, the left camera is usually the base camera. Yeah, and the transformation is between what we call the optical frames. Yeah, the optical frames from the frame of the optic. And if we, one assumption that we have is that those two the distance between those two cameras will never change. Right? So even if you move the cameras to another part of the robot, the distance between those two cameras should never change. Okay? If it changes, then you need to do this again. And the extra information that we need to get for stereo cameras is two rectification matrices, which we'll see more in a second, but it's what's the angles of the camera with respect to each other. And one baseline dimension, which is that distance between them. Okay. Okay, so in Gazebo we can extend the simple camera model to a stereo model by including one more camera. Let's look at that file. It's called multicam.model.sacro. Okay. Oh, I'll change that here. Okay, so this robot will be called stereo camera. Okay. For the first camera, we'll have a red colored camera. We still have the world link as before. And now, instead of having just a camera link, we have a left camera body. Okay, that's going to be the other one. And so here, the first joint that we have, which is fixed, is a joint between the world and the left camera body. This rotation makes it face down, and it's going to be 50 centimeters above the ground. Then we have the right camera body. Okay, and here we're creating a left camera optical frame. Oh, this is something that I need to explain a little bit later. Later in the presentation, we'll see that this Gazebo plugin had some also bugs, and it doesn't make it easy to find the baseline. It doesn't make it easy to find the transformation directly from the left camera frame to the right camera frame. So what this code is doing is putting one more frame in the middle and doing a transformation from here to here and then from here to here to find that transformation. That's why this is here. But actually, we have three frames: the optical frame, the reference frame, and the middle reference frame. So there's a few more joints that are connecting these three together. Okay. Normally, this should not be here. This is because there's a bug in the transformation. At the end, we should have the right camera joint connecting the right camera body to the left camera body, but it's connecting it to the optical frame and so there's like a translation in the x direction of 2 centimeters. You'll see this if you try to study this a little bit more. Then we have the plug-in. First we start with a left camera reference frame as a reference frame for the multi-camera. That means the left camera is the base camera, that everything goes from there. This sensor type is called multi-camera, but we'll use the name stereo camera. Update rate is also 30. Camera name left, field of view 0.6 radians. This is the dimension, the clip. And then we have right camera. And here the pose is being changed with respect to the left frame and the Y direction by 20 centimeters. Same field of view, same information here, no noise. And then we need the multi-camera plugin. We call it Stereo Camera Controller, which helps us to publish the topics, set the reference frame. And here, here's the 5 distortion parameters set to 0. And there's a baseline of 0.02, which we also see here. I think this is the same number. Right, so we have that. And we can run it by this command. Oh, this is an explanation, but we can run it here. So let's try that. Multicam. So simple camera model, multicam simulation. Okay, so here's the 2 cameras. The left one is the red one, the right one is the gray one. And another thing that was done inside this ROS launch file is that we started a node called the Robot State Publisher. This is a very useful and standard ROS node. Let's see what it can do. For example, if we say ROS node list, we see that we have Robot State Publisher here. Okay. If we say ROS node info Robot State Publisher, we see that the publication is TF and the subscription is joint states. So the input is a joint state. The output is TF. TF, we have studied that in chapter 4, some of us. TF is going to give what kind of information to us?
Right.
The pose of the links. The pose of the links. So basically you're getting a joint angle in and you're getting a pose out. It's a little bit like forward kinematics. It's forward kinematics, sorry. Yeah. If we say run the RQT graph, let's look at this. Yeah, it gets the joint states from Gazebo and it publishes TF out. Let me see. Where's doesn't show TF here? No TF here. If we say ROS run TF view frames, let's see what kinds of TF frames we have coming out of this. Evince is a program in Linux to look at PDFs. The ROS run TF view frames creates a PDF. So this is what we have. This is created by Robot State Publisher. Yeah? But Robot State Publisher needs joint states. What do we have here? We have the world link. We have the left camera body link. We have the right camera body. Now, and ideally, we should just have left camera body and right camera body. But these guys in the middle were created to assist with the bug that I will explain a little bit later. So that's the frames. Now let's go back here. And it says launch file also starts Robot State Publisher. It publishes the transforms. And this enables RViz to display frames of interest. Yeah? The figure on the right shows the left optical frame with respect to the world. So if we go back here, we can say Rust run RViz. Yeah, it starts empty. Yeah. And we need to set the right fixed frame, which is the world. Okay. Now it's empty because we don't have anything. The next thing we can try to add is the robot model. Yeah, that shows you the cameras. Okay. Actually, let me change this color to white. It's easier for you to see. Okay. And then we can also add axes, for example, directly. We can, for an axis, it takes a fixed frame. So for example, you can say world length. You can make that smaller, 0.5, radius. You can just make them a little bit smaller so you can see. So this is from the world, right? Then we can add another axis. This one can be related to the left camera body, for example. 0.5, 0.01. And you can see the left camera body the way that it's pointing. That's different from the optical frame. So look at the colors. This one has red pointing down, right, which is X. RGB is XYZ. The optical frame, remember, is the Z-axis, should be pointing out of the camera. In this case, it's pointing down. RGB, B is Z-axis. Z-axis is pointing down, right? So this optical frame would be what it belongs to the diagram that we saw earlier in our presentation when we were doing the math derivation. Then we have this mid, which changes. We have this reference frame, which changes, and then the right camera body like this. All right, so that's what we have. Question. I know, Jack, you're falling asleep. Robot State Publisher. Let me write it like this. Yeah? What is the input of this? What's the input? The input of this is what? Again? X? X? No. What's the output? Robot State Publisher. I just spent 10 minutes on it. No. What's the output? The output is TF. Yeah. These are the frames for the links. What do we get here? I said this is some kind of forward kinematics, right? What do you need? No. This is a camera. It doesn't have joints like a robot arm. What does joints mean here? We have how many joints? Well, we have at least two between the world and the left camera body, remember? And then we have another one between the left something something and the right camera body, right? Yeah? From the sacrophile? Yeah, these are fixed joints. Yeah, so this joint, they come in here. You look at their transformations, and then this publishes to TF. That's why you can see them. That's why you can see them in RViz. If you don't have Robot State Publisher and you don't have TF, you won't be able to see them. Questions? Guys, I spent 10 minutes looking at it. No one can say much, just quiet. What's going on? Yeah, are you guys taking notes, anyone? No, no one is taking notes. Oh, okay. I recommend taking notes. Okay. Active thinkers, not passive thinkers. Passive thinkers cannot answer questions. So for the stereo case, and we think about intrinsic camera parameters, there's some parameters that are going to stay the same. Focal length, central coordinates, and the K and R matrices, which have central point of the image, focal lengths, like that. The differences for the stereo camera compared to the monocular camera is in the projection matrix P, okay? The right camera P matrix will have a translation term on the first row and the fourth column. Yep. This P matrix, if we look at it before, it also has the focal length, it also has the central point for the image, and then we have a 0 at the end. That, for the right camera, that number will not be 0 anymore. It's a translation term. That translation term is computed FXB in the negative direction. So Fx is that focal length in the x direction over here. B is that baseline distance that we set up before, right? It's the distance between the right camera and the left camera optical frames. And so this gives you a pixel, I think, representation for that distance, for the intrinsic camera parameters. We also talked about the rectification matrices that we need. So the rectification matrices do a transformation from left to right or right to left of the images. What does that mean? I have a camera here that's looking at my hand. And I have a camera here that is looking at my hand. When you look at those two images, do they look the same? Slightly different, right? It's like you're looking from this side and then you're looking from this side. What we want to do is kind of make as if both, we want to align both images and match the points. We call this, imagine we have a virtual camera. And what we would imagine these virtual cameras to be is that they're perfectly aligned. So that means the image planes are on the same plane. They're exactly coplanar. That may not be true in reality, right? You have the right and the left. They may have some slight variations. The virtual cameras should be perfectly aligned on the same plane. Their optical axes should be parallel to each other. If there's any little difference, right, they wouldn't be parallel. But the virtual cameras need to have parallel optical axes. The x-axis, which is pointing this way, I think, or maybe pointing down, they need to also be parallel to each other, collinear. Yeah. So the rectification matrix is going to look at the images, and based on that create a transformation that sets the two cameras to be virtual cameras with these properties. When you do that, then you have the perfect alignment lets you know, for example, if my left eye is looking at this camera and maybe I'm focusing on this point, I can find the exact same point with my right eye, where both cameras are looking at the same point without any confusion or error in the distance. So here that's called correspondence simplification. For any M is the point in the 3D world. For any M point in the environment, the projection to the left or to the right virtual image needs to have corresponding, this should be U and V values. The U and V values should be identical. Sorry, I need to change that. So it's as if you take these two cameras and you put them behind each other. So when you're looking at an image, right, and you look at a point, both of them will have the same U point and the same V point. Yeah, which then allows you to work with both cameras together in a good fashion. So what we need to do as before is load the cameras, load the checkerboard, move the checkerboard, and perform the calibration. The steps are before. This is how you start Gazebo. Add the checkerboard, move it. But for the calibration node, we need to add more information. We need to say, for example, what's the topic for the right camera? Which, by the way, we haven't analyzed yet. Let's take a look. If I say ROS topic list, now, based on the Gazebo plugin, we don't just have something that says simple camera anymore. We have stereo camera with a left name, and then stereo camera with a right name. Same topics as before. The ones that we care most about is camera info image raw, camera info image raw. Correct? So here we need to say right, stereo camera, right image raw, and for the left, stereo camera, left image raw. Then, this is, I think, the namespace for the right camera, stereo camera right, and for the left, stereo camera left. These three statements at the end, fixed principal point, fixed aspect ratio, and zero tangent distance, are arguments that this calibration uses for some assumptions. Those assumptions, let me see what happened here, are described here. The fixed aspect ratio assumption is saying that the focal length in the x direction is the same as the focal length in the y direction. It reduces the number of unknowns and makes it improves results as long as this assumption is close to the truth. Yeah. Zero tangent distance says not to use tangential distortion, and fixed principal point says that UC and UV will be in the middle of the image plane. So these are some kind of fix, yeah, some kind of assumption that allows for a faster and more reliable calibration. Okay, let's try to run it. So let's come over here to Gazebo. Let's bring our terminal down. Okay, now you guys help me with the book. Let's see, maybe I have it here. The 4 things that we want to run is start moving. Oh, we need to add the checkerboard here. ROS launch, simple camera model at checkerboard launch. Okay, we have a checkerboard here. Then start moving it. Example, camera, calibration, move the checkerboard. So we start moving that checkerboard in front of the two cameras. And the last one is running the whole thing. So this will take a little bit more time to run, to write, see if I make any mistakes. Camera calibration, camera calibrator.py, size 7 by 6, square 0.01. We need to remap the topics. So right is stereo camera right image raw, left stereo camera left image raw. These are remapping of the topics. And then we need the namespace, right camera equals stereo camera right, and then left camera equals stereo camera left. And then all the fixes, fix principal point, fix aspect ratio. Hey, I have a mistake. No one fixed it. No one told me. I saw another mistake here. You guys are not helping. Hey, another mistake. Still not helping. I fixed 4 mistakes by myself. Oh, another mistake. Aspect. Okay. Thank you. You guys were very helpful. So, you know, we wait, right? Those assumptions make this run faster, but again, remember, they only work if the true case is similar. If the true case is not similar to that, and you're making those assumptions, you'll make big mistakes. Notice how at some points it places circles at the intersection of the checkers and connects them with lines, right? So it's how accurately it can do that based on the internal intrinsic parameters. So you'll want to run this in Baxter UR5 for any kind of final project. Rotau has a very nice routine. Instead of a human holding that, you put the checkerboard on the robot hand, because you want to do something related to that. That's extrinsic calibration, sorry. And then moves the checkerboard, does intrinsic and extrinsic together. Yep. So we need to wait, see if this functions. So this time when we save and commit, it's supposed to save ROS camera info, stereo camera right or left .yaml, and save the camera info parameters there. Here, let me just talk about the results for a second. Rectification matrices, right? It says that here these matrices are almost identity matrices. Well, almost means, what's an identity matrix? 100, 010, 001 for 3D, right? So instead of being 100, it might be 0.9900. That's what almost means. And if you have something that's close to the identity matrix, what does it say about the transformation between the virtual cameras, or between the cameras? What does it say? I have a camera, and I have a virtual camera. The camera should be transformed to become the virtual camera. Yeah, maybe I'll draw it like this. Maybe two colors. Let's say that if you could zoom in, maybe the left camera looks like this, the right camera looks like this. Okay? They need to be coplanar, collinear, right? So the virtual camera should kind of look like this. And basically you could say, oh, these two are parallel. Yeah? And the kind of this line here is perpendicular on both sides. And then if you have an axis here, they're also parallel. X, Y, Z, whatever, right? So to take the blue camera, which is, this is the virtual camera, the other one is the real camera, you need a transformation. Yeah? So to take the blue and take it to the red. If the transformation matrix is an identity matrix, what does it say about the orientation? It's the same. It's the same. Why would it be the same? Here. Why would it be the same here? Because it's a simulation. And you can set things perfectly. But in real life, the two cameras will not be perfect. Yeah. So you won't get identity matrices. Okay, so you click calibrate. It's running the routine internally. If you want to know more about the routine, you can go to OpenCV, calibrate. On YouTube, there's many, many videos, I'm sure Baidu, about all the details of how to do this, okay? Now, it's taking quite a bit of time to do the calibration. It's not automatic. Still waiting. Okay, now we can save and commit. No errors this time, so let's go to ROS. See if we can see anything here. No, I don't see it. That part still seems strange. For temp. Let's look at this. This is new. It still put it in temp. LS, LT. Yeah, this one was just created a minute ago. So I can kind of put it here, ROS, stereo cam. Can you let me do that? CD ROS. There's stereo cam. Oh, remove cam, move, calibration. Oh, I deleted it by mistake. Okay, oh no, wait a second. Here, I think I deleted it by mistake by changing its name. Anyways, you can go back and do the same thing. And basically, we're going to do the same thing, compare focal length, central image points to what we created, and do that. Baseline distance. Guys, there's another thing that Professor Wyatt Newman created here. He calls it an alternative multicam model. This one was done to overcome the problem of the frames that I described earlier. Here it says, one complication of the multicam model is that the libgazebo ROS multi-camera plugin has a non-intuitive specification of the frames. It was necessary to include intermediate frames to achieve desired poses and image orientations. So the alternative version is using 2 monocular cameras. So we looked at one camera and then we looked at multi-camera, right? Plugins. So now what we're going to try to do is use 2 monocular cameras and put them together to do the calibration. When we use 2 monocular cameras, it's more intuitive to do frame specifications, and the topics don't come as stereo, they just come out as left and right. The difference here, although this is another problem, is that each topic has a different time stamp. The time at which you publish is not the same for both of them. So you need to find a way to make their timestamps agree. This will only work if you use static images. What is a static image? An image where objects don't move, don't change at all, because then the positions don't change, right? But if you have things where things are moving, then this technique will not work. If you have static images, in this program, what you can do is basically you compute a new timestamp and then copy that value to the messages that you're going to publish, and then publish them there. Something like that. I won't go through the details of the code or everything like that. You know the routine, but you would need to go back through the book and notice that this method is easier in terms of computing the transformation from the left camera to the right camera without intermediate frames. But it has a big problem, which is the time synchronization of the 2 topics. And this will only work for static images. So basically, you still got to work with the multi-camera plugin, but have to fix some intermediate frame creation to help you find the right way to create the frames later. Okay, now the last part is how do we use OpenCV in ROS? Now I'm going to skip this section from this book. In this book you'll get some maybe 3 or 4 examples to doing edge detection, this and that. You can read it, but what I'm going to do now is use another presentation that I've done in the past from the book ROS by Example, chapter 10. Okay, so